Hello everyone, welcome to the lecture 4 of week 2. So here we are discussing about deep learning fundamentals, and in this lecture we will discuss about backpropagation. That's the central idea for training the deep neural networks. So we will talk about computing gradients, and on a toy example we will see how this backpropagation algorithm works and what do we really do for a deep neural network for computing gradients. So this you will now find familiar, this particular picture. So this is an example of a deep neural network, and this is very similar to what we had seen in the last lecture. So you have 3 input dimension, 2 output dimension, and then you have 3 layers with 4, 2 and 3 neurons each, and you can compute the number of parameters that you need. You can also write the equation. You can say, okay, H1 is value of beta naught plus gamma naught x, H2 is nonlinearity over beta 1 plus gamma 1 H1, right. S3 is nonlinearity over beta 2 plus gamma 2 H2, and you see the consistency in our notation, and this also helps you write it nicely. And then finally, my function is beta 3 plus gamma 3 H3. Right, that is my final output y. Now, for computing gradients, what do we need to do? First of all, we have to compute the loss of the network. So because we are getting these outputs, so we can compare them with the ground truth and compute what is the loss of the network. So we compute the loss of the network, we sum it over all the I training examples that we have seen, and then once we have computed the loss, we do stochastic gradient descent. So that is, the new parameter set is the previous parameter minus I go in the opposite direction of the gradient. So that is learning rate times partial derivative of loss with respect to each parameter, right. So this is what I do, right, and this I can do it for the entire batch, or I can do it over few examples. So this is like a particular batch is what I have taken. We will see these notions fully in the next lecture. We will define this, what do I mean by taking a batch only compared to the entire set of examples. So in this case, these are our parameters. Now they are not scalars, there are some are vectors, some are matrices, right. These are our parameter set. So I need to compute, to be able to update my parameters, I need to compute, so the loss, the derivative of the loss with respect to each of these over beta k, where k varies from 0 to 3, and loss over omega k, where k varies again from 0 to 3. So I have to compute all of these. So once I have these individual derivatives, then I can update my betas and omegas, right, to the next better value, and I keep on doing that. So for doing that, I need to compute the derivative of loss with respect to these parameters. Now, why is that such a big deal, right? So if you want, you can actually open this whole network and write it as a simple equation. So y prime, not a simple equation, but an equation, right? Y prime as phi naught prime plus phi 1 prime h1. So h1 can be a of phi 1 naught plus phi 1 1 h1. So this was h1 prime, and h1 prime in terms of h1, right? So h1 in terms of a theta 1 naught plus theta 1 x. So like that, you can open the entire equation and write y prime as a function of x, right? So you're applying nonlinearity twice to get this, but it's just an equation in x and all other parameters. But this becomes a huge equation, right? And we need to compute derivative for each parameter, right? Whatever parameter you are seeing, and every point of your batch and every iteration of the stochastic gradient descent. So we need some standard way of doing that, and that is where the backpropagation algorithm comes very handy. It's proposed in 1986 among others by Hinton, right. So, what is the idea? So, let us first see the intuition for backpropagation and then we will see the algorithm in detail. So, we are into the same. So, now we have 3 hidden layers. I have the input and I have the output, right, and output will be a function of x and the parameters, and I have my ground truth. So, I'll somehow compare the output with the ground truth to compute the loss, right. But my task is compute the derivative of loss with respect to each of the parameter. Yes. So, what does that mean? So, let us take this parameter, right. So, to compute the derivative of loss with respect to this parameter means I want to say how a small change in this particular weight, right, would impact my loss, right. So, how this small change in this weight feeding into H1 modifies the loss, we need to know. So, if we make slight change, it will change, right, and then how this change in H1 will impact the layer H2, and how will that change in H2 will impact H3, and how will that impact in H3 will change your final output, right, and how will this output change will change your loss. So, it goes through multiple steps, right. So, how a small change here will actually keep on moving forward to modify your loss. Okay. Now, the way we do it, so we will see a toy example first and then we will come to a deep neural network, that how this backpropagation is actually done. So, we will see a simple equation here, right. So, all are scalars. So, a function of x and phi. So, it's beta 3 plus w 3 cosine of beta 2 plus w 2 exponent beta 1 plus w 1 sine of beta naught plus w naught x, right. And let us say this gives you f x phi given an input x, right. It is a scalar, it gives me a final scalar output, and I have my ground truth. So, for any x I can compute f x I phi as the output of this model, and I have my ground truth. So, I take the mean square error loss, right. So, squared error, and this is my loss, right. Now, I want to see how a small change in each parameter will impact my loss, right. So, let us say how a small change in beta 3 will impact my loss. So, partial derivative of loss with respect to beta 3, right. Right now, I can see loss as a function of f x I phi minus y I square, but how would I compute dou of L I over dou of beta 3. So, for that what we typically do is to write this as a series of intermediate calculations, so that I do not have to directly take a derivative of the entire expression, because that will be cumbersome and also error prone, right, and we will be doing certain things again and again and again, right. So, we want to make it modular. So, we say okay, let us write in terms of modules, simple modules. So, we say okay, so this beta naught plus w naught x is my f naught. So, this is my f naught, then this whole thing is beta 1 plus w 1 sine of f naught. So, I call this sine of f naught as h 1, h 1 is sine of f naught. So, now this becomes beta 1 plus w 1 h 1, right. I call it f 2. So, this is was f naught, so I am calling it f 1. So, f 1 is beta 1 plus w 1 h 1, right. This whole thing is now f 1, right. Again exponent of f 1, I call it h 2. So, this is my h 2. Now, beta 2 plus w 2 dot h 2, I call it f 2. So, f 2 is beta 2 plus w 2 times h. Cos of f 2, I call it h 3, and beta 3 plus w 3 h 3, I call it f 3, right. F 3 is the final function, right? And my loss is f 3 minus y I square, that is my loss. It's very modular, I mean, and you see each f I has very similar form. So, whatever I do over one f I, I can actually take it for other f I's also. I do not have to redo everything. And this I can see as a nice computational graph. So, I started from xi, xi gave me f naught gave me h1, f1, h2 and so on up to I got li, right. So, this is my forward propagation from simple xi to going to the loss, a forward propagation. Now, when I compute the loss, this is called the backward pass. So, I do this calculation backward. So, I compute the derivative of loss with respect to each of these intermediate quantities, right. So, this was my quantity Li, F3, H3 and F2. So, what I will do, partial derivative of loss with respect to F3, then with respect to H3, F2, H2, F1 up to if I need to Xi, right. So, this is what I will do, right. So, I will go backward and compute the loss, derivative of loss with respect to each of these quantities. Now, how exactly? So, first thing I have to compute derivative of loss with respect to F3, right. Now, this is what I have to keep handy, my forward propagation. Now, this I will start with the last thing, right. So, that is why I am going backward. Now, this is very easy, derivative of Li with respect to F3 is nothing but 2 times F3 minus y, right. So, one part done, right. So, then I have to go and say what is derivative of loss with respect to H3, right. Now, that is where the chain rule comes in handy. So, dou of Li over dou H3. Now, I already have computed dou of Li divided by F3. Now, I will simply compute dou of F3 divided by dou of H3 and this will give me the final output, right. So, this I have already computed and this I will compute, and I can compute it because I have written F3 as a function of H3, right. So, this dou F3 over dou H3 is nothing but W3, right. So, and this I keep on doing further and further. So, this I went up to here dou of Li over dou of F3. Next, I will compute dou of Li over dou of F2, dou of H2, F1, H1 and F naught, right. So, I will compute one by one, right. So, I go backward. So, we did up to H3 here. Now, from H3 we are going to F2, H2, F1, H1 and F naught, right. Every time it is just chain rule of probability, chain rule of derivation. So, dou Lf by dou F2 will be nothing but dou of H3 over dou of F2 and dou of Li over dou of H3 that I have already written as dou of F3 over dou of H3, dou of Li over dou of H3, and this is what gives you this quantity, right. So, I just add one quantity at a time, right. So, I have already computed this previously. Now, I will add this quantity and multiply, right. So, it becomes very modular. Now, I have computed all three. So, I will just add one more quantity to multiply and I get the derivative for everything. Okay. So, we will get it for all the intermediate quantity, right. But what we finally need, right, we want these are my parameters, like the proxy parameters in this toy model, betas and W's. So, how would I get? So, partial derivative of loss with respect to all these Wk and all these beta k, right. So, dou Li over dou of Wk. So, for that I can see, right, I have done it for all these, right. So, I have also done it for dou Li over dou Fk, and then by again using chain rule I can say dou of Fk over dou of Wk, and this gives me this quantity. So, this I have already computed, this is the new thing I have to compute. Same way for beta k, I will do that, dou Li over dou Fk is done. Now, I have to compute dou of Fk over dou of beta k. So, given this I have to now compute two more things, that is all, right. So, wherever I have dou Li over dou Fk, I use that to compute dou Li over dou Wk and dou Li over dou beta k, and that is all. That will give me all the derivatives that I need, right. So, this was my going backward, and now every time I have dou Li over dou Fk, I also have two branches to give me dou Li over dou Wk and dou Li over dou beta k. And this I do for k is equal to 3, k is equal to 2, going backward, k is equal to 1, k is equal to 0. And this gives me derivative of loss with respect to each of the parameters of my model. Okay. Now we can see what happens in my actual deep neural network. So now I will not be dealing with simple scalars, but I will have these matrices and vectors that are getting multiplied. So this is my training input x, my hidden layer h1, h2, h3, my output, and the loss, right. I will follow very similar strategy. Because of our simple notations, I will write this entire forward propagation first, right. So I will say okay, f naught is beta naught plus omega naught xi, right, and then I apply nonlinearity over there. So this gives me h1. So this is my f naught, and I apply nonlinearity. This gives me h1. So h1 is nonlinearity over f naught, right. Now I am at h1. So again I will do f1 is beta 1 plus omega 1 h1, okay, and h2 is nonlinearity. h2 is nonlinearity over f1. Again I have got h2, so I will say okay, f2 is beta 2 plus omega 2 h2, and h3 is nonlinearity over f2, and f3 finally is beta 3 plus omega 3 h3, and this is what is my output. I do not apply any nonlinearity here. This is my output, and I compute loss over this f3 and yi. This gives me the loss function. So this is the forward propagation. Now what I have to do, so this we have done successfully, series of intermediate calculation. We used pre-activations. So this was my pre-activations. F's are my, if you see f0 to f2 mainly are your pre-activations, and correspondingly we got h1 to h3, that were my activations. They were my activations. Right. Now my parameters are all these betas and omegas. So I have to compute the loss, derivative of loss with respect to each of these parameters, right. And for that, what I will do, I'll follow the similar path. I'll compute the derivative with respect to each of the intermediate quantities that I have described. So and going backwards, so I'll say okay, derivative of loss with respect to f3, loss with respect to f2, f1, and f0, right. So I have not shown this, but when you go from f2 to f3 to f2, you have to go via this h3. So dou Li over dou f3, dou f3 over dou h3, dou h3 over dou f2, right, like that. Now, and yeah, similarly dou Li over dou f1, you will have another two terms that are getting multiplied, and so on. So this is how you can express your derivative in terms of all the intermediate quantities, right, based by chain rule, and you can keep on composing things by adding two more things. Now the question is, this was easy when they were all scalars, but now dou f3 over dou h3, what is that? Now my f3 is my output. So f3 is two dimensional, and h3 is three dimensional, right. So what will be this? F3 is two dimensional, h3 is three dimensional. So what will be dou f3 over dou h3, right? Partial derivative of f3 with respect to h3. They are no more scalars, they are different vectors, right. So how do we write it for vectors? So a little bit of matrix calculus. I mean, so let's say you have a vector A, right, four-dimensional vector, and you want to write f is a simple scalar function. You want to write derivative of f with respect to A. So you have to have the components as per the input. So dou f over dou A1. So this is, we will follow something called denominator layout. So it follows the denominator. This has four rows, right. So it's a column vector. So this also became a column vector. Dou f over dou A. Similarly, what if A is a matrix, right? So it's a function of a matrix, and have to do dou f over dou A I will simply follow this layout. So, this is 4 cross 3. So, dou f over dou a will also become 4 cross 3, same dimension as the matrix A, 4 cross 3, right. So, this is again denominator layout. Now, what if my function is a vector, f is a vector and a is also a vector. So, what will be dou f by dou a? So, in denominator layout, I will still follow the same number of rows as this column vector. So, I have 4 rows h per a, and this f gets absorbed in the columns. So, 3. So, it is a 4 cross 3. So, f is of 3 dimension and a is 4 dimension, I get 4 cross 3 vector, right. And this gives me some idea of what I will do with my original question, where I had 2 dimension, 3 dimension. I'll follow this denominator layout, right, 4 cross 3. Okay. So, now you can try to compare what happens if you do derivative for a scalar versus matrix. So, here if my f3 was beta 3 plus w3 s3, if I got partial derivative of f3 with respect to beta 3, it will be simply dou over dou w3 beta 3 plus w3 h3. Okay. Now, I think here I should write beta. So, dou over dou beta 3, and this, if you get beta 3 with respect to beta 3, this becomes just 1. Okay. Now, in terms of matrix, what will happen? So, you have now matrix notation, the vectors f3, beta 3, omega 3, s3, they are vectors or matrices. So, if I compute dou of f3 over dou beta 3, it will be dou over dou beta 3, beta 3 plus omega 3 s3. Beta is a vector, right, and this you get as an identity matrix. Now, why is that happening? So, you can try. So, let us say this is some m cross 1, this is also m cross 1, this is m cross n, and this is n cross 1, right, and I am doing dou f3 over dou beta 3, right, dou f3 over dou beta 3. And as you understand, that will be 3 cross 3 matrix, right, because f3 is 3 dimension and beta 3 is 3 dimension, it will be a 3 cross 3 matrix, right. But what will be the output? So, f3 is equal to beta 3 plus omega 3 h3, right, and let us say this was 3 cross 1, 3 cross 1, and this will be something. Now, this will not matter much, right. So, so what I will have dou over dou beta 3. So, let us say beta 3 is some d e f, and this quantity will have some more things, but what I am concerned right now is this beta 3 d e f. So, when I take the derivative of beta 3 with respect to beta 3, I will get derivative of d with respect to d, and I will first use this layout, right. So, dou of d over dou of e, dou of d over dou of denominator layout f. Now, I will go to the next one. So, dou of e over dou of d, dou of e over dou of e, dou of e over dou of f, and then finally dou of f over dou of t, dou of f over dou of e, dou of f over dou of f, right. So, please remember, so you are following the denominator layout. So, this will change as per this denominator d e f, right, and here this is changing as in the row, in the columns. And now, if you want to compute this quantity, this will give you 1, this is 0, 0, 0, 0, 1, 0, 0, 1. So, you get an identity matrix. that is a derivative, right. Similarly, what would happen? So now I am saying F3 is beta 3 plus W3 H3 dou F3 over dou of H3. Now here this will not matter, so I'll consider about this quantity. If this is scalar, I simply get as W3. But what will happen if this is a vector, right? So if it is m cross 1, m cross 1, m cross n, n cross 1. So dou F3 over dou H3, right? So F3 is m cross 1 and S3 is n cross 1. So we know in denominator layout, I'll get n rows as per the denominator and I'll get m columns. So it will be n cross m matrix, right. And if you see in terms of dimension, it matches. So omega 3 transpose is n cross m, right. So it matches in terms of the dimensions. But how do I explain this? That when I do derivative with respect to S3 of this whole quantity, I get omega 3 transpose, right. So we can just have a quick look at this. So we are again using m cross n and n cross 1, right. So dou F3 over dou S3 will be, so F3 has m things, so dou F3 1 over dou H3 1, dou F3 the first dimension divided by dou H3 2 up to I go to n, right. Dou F3 1 over dou H3 n, and here I will get dou F3 m over dou H3 1, dou F3 m over dou H3 n, right. This is what I will get. Now let's try to compute like some of these elements. So what will be dou F3 1 over dou H3 1? So F3 1, the first quantity will be, so now omega 3 1 1 H3 1 plus omega 3 1 2 H3 2 omega 3 1 n H3 n, right. Now if I do partial derivative of F3 with respect to H3 1, I get omega 3 1 1. So here I will get omega 3 1 1, right. Now let's see F3 1 with respect to H3 2. So I will get omega 3 1 2, right, and immediately you can see why we are getting a transpose. So 1 2 should have been here, but I am getting 1 2 here. So omega 3 1 1, omega 3 1 2, and similarly for m you will get. So if you look at F3m, so F3m will be omega 3 m1 H3 1 omega 3 mn H3n. So if I do partial derivative of F3m with respect to H3 1, I will get omega 3 m1. So this I will get omega 3 m1, right. So but originally what was omega 3? Omega 3 was omega 3 1 1 omega 3 m1 omega 3 m cross n, so n1 and omega 3 mn. So you are getting just a transpose, right. m1 is here and m1 is here. So omega 3 1 2 is here, but you are getting 1 2 here. So you are getting a transpose of omega 3, right. So that explains this particular output. So we learned how to compute this. Dou F3 over dou S3 is nothing but omega 3 transpose. So like that you will have to go a bit into the vector calculus, and then you can compute all of these. But once you compute one, so it just follows by symmetry to other cases, right. Now other thing you have to do is to compute the derivative of the value. Now this is also not very difficult. Let's say we have a as a value of b, and A and B are both vectors. Now we could equivalently write A1 as value of B1, A2 is value of B2, A3 is value of B3. Now I want to take derivative of A with respect to B. So again follow the denominator layout. So you see B1, B2, B3 is being followed like that, and A1, A2, A3 like that, right? Now when I do dou of A1 with respect to B1, I'll say okay, value B1 over B1, right? And there if B1 is greater than 0, this will be 1, otherwise 0. So I can simply write as an indicator function if B1 is greater than 0, right? So this quantity will be B1 over B1, otherwise it will be 0 over B1, right? So I'll get it 1 only if B1 is greater than 0. That's the indicator function. And here A2 over B1 will give me 0 and so on. So only the diagonal I'll have the indicator. If this is greater than 0, I'll get 1, otherwise I'll get 0. So this is as if you are multiplying pointwise by this diagonal indicator of B greater than 0. That's what will be the derivative of ReLU. Okay. So F2 greater than 0. Right. So H dou S3 over dou F2, because S3 is nothing but ReLU of F2. So this derivative will be indicator function of F2 greater than 0, right. So now if we just use these ideas together, then derivative of loss with respect to beta k will be dou Fk over dou beta k, dou Li over dou beta k, and this we have seen is nothing but identity matrix. Multiply with this, you get dou Li over dou Fk, that you will anyway compute in the series of computation. And dou Li over dou omega k will be dou Li over dou Fk times Hk transpose, and then we saw, right, how this will become Hk transpose, and that's all you need, right. So this you are anyway computing intermediately, and then you have formula to compute it for omega k and beta k. Beta k was simply this, and omega k was Hk transpose. So in forward pass, I will say okay, f naught is beta naught plus omega naught xi, and Hk is a of Fk minus 1, the ReLU nonlinearity, and Fk is beta k plus omega k Hk. So like that I write the forward pass. So starting from xi, I get f naught, h1, f1, h2, f2, h3 up to I get Li from the last f. And then I do backward pass in the for propagation, and there I go back. So dou Li over so I'll compute dou Li over dou Fk, and from that I'll compute dou Li over dou beta k, dou Li over dou omega k, right. So dou Li over dou beta k we found was simply dou Li over dou Fk, and dou Li over dou omega k was dou Li over dou Fk times Hk transpose. And then how do you go dou Li over dou Fk minus 1? So from these, so this is the indicator function for ReLU, element wise multiplication to omega k transpose dou Li over dou Fk, right. So these are all equations, you have to keep on doing it for all the layers, and this gives you the backpropagation. So you can compute the derivative of loss with respect to each of this Fk and beta k and omega k, right. Now we did that on paper, I mean on slides, but you don't have to actually code for all this in the modern frameworks, because what they do, they can compute these derivatives automatically. So what you have to specify is your model and what is your loss, and the technique by which this is done is called algorithmic differentiation. And how does that work? So each component knows how to compute its own derivative, right. So like ReLU knows how to compute derivative of output with respect to input, right. We saw the indicator function. Any linear function knows how to compute derivative of output with respect to input and with respect to parameters. So what we do, we just specify the order of each components, right, the forward pass, and the algorithmic differentiation has inbuilt this doing the backward propagation by taking the chain of derivatives. And even if you have branches, it does not matter as long as there are no cycles, right. For any acyclic graph, you can easily code this. So you can read more about it in chapter 7, and we will have one more lecture for this week. We will discuss about different sort of methods for computing gradients, right. So stochastic gradient descent and Adam and other kind of methods. Thank you.